Justin.
Oh, yeah, so for our second presentation of the day, this is the group that Mike Wong and I led. And so Kat, Ross, Linus, and Srikar are going to be talking about non-left-orderable surgeries and
Hi, I'm Justin.
I'm Linus. I'm Srikar.
And I'm Kat, and we're going to be talking, as Jen said, about non-left-orderable surgeries on twisted Torus Knots. So just a brief roadmap of what we're going to talk about. First, we're going to sort of motivate the results that we've been getting, which are about what's called the Boyer-Gordon-Watson L-space conjecture. We're going to talk about the specific cases in which we study this conjecture, which is Dane surgery on twisted Torus knots. We're going to talk a little bit about previous results for these specific cases. And then we're going to talk about our results and a little bit about our methodology, and then maybe some things that have yet to be proven. So let's start with left-orderability. We say that a non-trivial group is left-orderable if there exists a strict total order on the group, essentially which respects left multiplication within the group. So if G is less than H, then FG must be less than FH for any F in the group. An example of a left-orderable group is Z under addition, just with this standard order. We all know if you have an inequality, you add the same thing to both sides, surely you must get an inequality that's still true. And a non-example is actually Z mod M under addition. In fact, you can prove that any group which has a finite order element has to be non-left-orderable. We can do this. We say some group G, an element in our group, I don't know, say that of order N. G must be either greater than or less than the identity, right? Without loss of generality, assume it's positive, greater than the identity. So if G is greater than 1, well, we know that this is, if we assume we have left order, sorry, G is greater than 1. Well, now we can multiply on both sides by G, so you get G squared is greater than G. But we know that G is greater than 1, so G squared is greater than 1. We can sort of see if you keep multiplying by G, you'll have to get up to G to the n is greater than 1, but this is 1. 1 can't be greater than 1. So in fact, this proof demonstrates that Z mod M and any other group of finite order elements is not left-orderable. Now we're going to talk about the Heegard-Floer homology. If you're familiar with algebraic topology, you might suspect that this homology would associate a vector space or a sequence of graded groups to some kind of topological space. In this case, we're interested in 3 manifolds as our topological spaces, and the Heegard-Floer homology will associate a vector space with coefficients in F2 or Z mod 2. And so we say that a closed connected orientable 3 manifold is an L space if it has sort of the simplest possible Heegard-Floer homology. Now we have enough things to find to talk about this conjecture, which is the main conjecture that we've been studying all summer. This is due to Boyer-Gordon-Watson. It says that an irreducible rational homology 3-sphere is an L space if and only if its fundamental group is not left-orderable. So rational homology 3-sphere is just a particular kind of closed connected orientable 3 manifold. Irreducible just means that you can't sort of break it up as the sum of other manifolds. Here we're talking about the connect sum. And so these particular kinds of manifolds are conjectured to be L spaces if and only if their fundamental group is not left-orderable. And this is really noteworthy because the Heegard-Floer homology and fundamental group appear to be very different structures. So the idea that a property of one might be equivalent to a property of the other is a really non-trivial idea. And so this summer we were interested in trying to verify this conjecture for certain 3 manifolds, which I'm going to talk about next.
Great. So, as Kat said, the goal of our research is to help verify this conjecture. So in order to do that, we need to find some of these particular L spaces so that we can look at their fundamental groups and obstruct their left-orderability, thereby verifying the conjecture. So in order to get some of these 3 manifolds, let's start looking at knots, right? So a knot is exactly what you think it is. It's basically an embedding of the circle into S3 or R3. It's basically just a circle, but you could go under and over and get some structure like this. Here's another example of a knot. And our particularly interesting one is the torus knot. So what you do in the case of the torus knot is you take a torus, right? And you basically inscribe your embedding of S1 along the torus, right? So and particularly what you can do is you can take a pair, PQ, right? And as you wrap P times around this way, you wrap 2Q times around the meridian like this, right? And we call this the TPQ torus knot. So this is one picture of it. Another's like this. You can sort of also think of it as taking 3 strands, giving them 5-fold twists, and then closing it all up. So slightly more complicated than this is the twisted torus knot. So what you do in the case of the twisted torus knot is you take your TPQ torus knot, you take L of those strands, then you put N twists on them. And you can view this as sort of the knot sitting on a genus 2 land, genus 2 surface. So it looks something like this, and we call this the TPQ-LM torus knot. Okay, so now that we've got these knots, we need to somehow generate some 3 manifolds, right? And we do this by a process called Dane surgery. So what you do in Dane surgery is essentially, basically, let's say you have a knot. For simplicity, let's just say it's the unknot, or which is just the circle, and we have another torus over here. So if you take any knot, you thicken it a little bit. So, and this will go around like this. You'll get a torus, right, or something close to a torus with twisting around and such. Then what you do is you basically take the complement inside S3, right? So you get all this stuff around here, right? And so now you have S3, but it's missing a torus on the inside, right? So now what you have to do is, to make it slightly more complex, is you have to glue back in this torus somehow. So how do you do this, right? Well, if you want to glue back in a torus, right, you have to specify where where essentially the meridian is going to go, right? So basically what you do is, so if I can specify where this meridian is going to go, I'll be able to glue back in the entire torus. So this is basically specified by a rational number r, right? Because if I have a rational number r is equal to p over q, that'll correspond to basically, if I go q times around this way, wrapping p times around this. So it's the same concept as the torus knot, right? So I glue it back in like this, right? And basically, it'll take in this rational number r, which corresponds to the slope that you're gluing along, and this knot, and it'll give you a 3 manifold, right? So in a recent paper by Bafai, he showed that if you pick a sufficiently large rational number r and twisted torus knots of these forms, you will in fact get some of the L spaces that we are looking for. So the goal of our research is to basically obstruct the left orderability of the fundamental groups corresponding to these 3 manifolds, which we know GL and PQR. R is the rational number from knitted sort group. Okay, so before we can do that, we have to first compute these fundamental groups, right? So if you apply Srikar Van Kampen to the process of Dane surgery, you'll get that it's basically just the fundamental group of the knot group, which is, if you have your knot, you take its complement inside S3, the fundamental group you get from there, modded out by this relationship you obtain from Dane surgery, right? So in Dane surgery, you're gluing back in this torus along a slope of rational number r, right? So say you have generators mu and lambda basically corresponding to the torus that's sitting inside your original three manifold before you glue back in the torus. Then if you go along mu t lambda the v, which corresponds to moving along this rational slope, it's exactly like you're moving along this torus here, which will just go to the identity. So you just have to mod out by this relationship where mu and lambda are generators corresponding to the torus boundary, and you set that mu to the t lambda v equal to 1 and the ratio is equal to r. Okay, so mu and lambda are called the generators of this peripheral subgroup, which is isomorphic to z cross z because it's essentially a torus. Here's some pictures of the calculations we did. I'm not going to go into exactly what's going on here, but basically this corresponds to one of the generators of torus energy, and this kind of corresponds to the generator of the other one. And to talk about the fundamental groups we derived was
as Linus said, mu and lambda are the generators of the peripheral subgroup of the torus boundary. And so we derived the knot groups and the peripheral subgroups. Note that C here is an expression in A and B, and the C for the plus pk plus 1 case is in the same as the C for the pk plus 1 case. That's the groups. That's the case for pk plus 1. Right. So, where did it all start? We saw a paper by Clay and Watson, and they had a result for specific P, K, or M. Now, they either had to fix K or M, so we had to try to generalize that result for P equals 3. There was a lot of casework involved, so what we did was we considered cases where A and B were positive or negative, but it turns out you get stuck when A and B are both negative. So we were really stuck. And then a paper by Ichihara came out, which basically made all our results useless. Because they pretty much, the group we were analyzing was a special case of their general result. Right. So we were like, where do we go from here? So there was another paper by Lafai which divided all pk plus 1 L space twisted torus knots into 3 classes. L equals 2, and L equals p minus 2, m equals 1, and L equals p minus 1. So we wondered whether it was possible to use the methods of Ichihara and adapt them to the 3 cases of Lafai. And that's exactly what we did. Exactly. So the Klein-Watson's general case was just the first case of Lafai. And we did this first. Generalized. And our bound on R is larger than the bound obtained by Klein-Watson, so it's better. So we proved it for L equals p minus 2, m equals 1, and L equals p minus 1. But we weren't able to prove it for L equals 2, and that question still remains open. But the results we have so far support the L space conjecture. And that's where we are right now.
Okay, I'd like to talk about our methodology, how we got these results. Our method of proof relies on a different characterization of left-orderability than the one that Kat presented definitionally at the beginning of this talk. Basically, we can view countable left-orderable groups as subgroups of homeo plus R, and it will become clearer as I explain more terminology why this characterization really helps us get our results. To explain why, I need to introduce the definition of a global fixed point, which basically, if you have a group action, a real number, if you have a group action on the real numbers, a real number is called a global fixed point if the stabilizer of that number is the entire group. Basically, every element of the group fixes it. And the reason we care about these global fixed points is because of the following proposition due to Boyer, Wolfson, and Wiest, which basically says if you have a non-trivial group action, there must be another which is an action with no global fixed points. So I'd like to walk through our argument carefully. If we assume by contradiction that this quotient group associated today in surgery is left-orderable, then because it's isomorphic to a subgroup of homeo plus R, which is the group of order-preserving homeomorphisms of the real line under composition, I forgot to mention that before. But if we assume that this group is left-orderable by contradiction, because it's isomorphic to a subgroup of homeo plus R, there must be an injective homeomorphism from these groups to homeo plus R, which will obviously have non-trivial image. So therefore, there must be another such homomorphism which has no global fixed points. Therefore, to prove our results, it's sufficient to show that every homomorphism from these groups, homeo plus R, has a global fixed point. So the natural question to ask is, how can we prove every such homomorphism satisfies this condition? As Srikar mentioned earlier, Ichihara and Tema did a lot of work analyzing global fixed points. They basically said if you have the knot group in a specific form, then every homomorphism from the corresponding quotient group after Dane surgery to homeo R plus will have a global fixed point, and by the same argument that I walked through earlier, hence will not be left-orderable. But unfortunately, the condition that the knot group is of this form seems to be a little strict. We were able to generalize Clay and Watson, just applying their theorem directly, but to extend to the results that we actually have, which are much larger classes of L-space twisted torus knots, we needed to modify Ichihara and Tema's conditions a little bit. So our main theorem is a modification of Ichihara and Tema's, which rather than require that the knot group be of a specific form, just imposes these two conditions. That S is a word that contains all positive powers of your generators, and that all homomorphisms from the surgery groups to homeo R plus satisfy this condition. These conditions actually turned out to be a lot stronger. We were not only able to further generalize Clay and Watson, but prove the second theorem that was presented earlier, which is an entirely different class of L-space twisted torus knots specified by Buffet.
So just some outlook on after we've gotten these results, what's sort of still left. So I'm going to go a little bit out of order here. As Srikar kind of mentioned before, this theorem by Buffet gives these three different cases of twisted torus knots, which when you perform some kind of surgery on them, given L space, we had these two results for the first two cases. We haven't proven the third case, which is when you take these two strands and you twist them one full time to get the twisted torus knot. And secondly, we can talk about, so all of the theorems that we presented, including and also those by Clay and Watson, said for a sufficiently large surgery slope, we get a fundamental group, a manifold whose fundamental group is not left-ordered. And it turns out, if you have a knot which does permit a surgery that gives an L-space manifold, there's a similar bound where for all surgeries greater than or equal to some certain number, you will definitely get an L-space. For anything less than that, you will not get an L-space. And so it's worth comparing whether or not, if we really want to verify this conjecture for all the cases we can, we would like those bounds to line up so that every surgery which is an L-space would also have a fundamental group that's not left-orderable. It turns out that the lower bound that we get, and also Clay's and Watson's, which is sort of just ours is sort of just a generalization of their bound. It turns out that the bound that we all get is slightly larger than the minimal bound on the surgery to produce an L space. And so that means that there are a lot of surgeries which we actually know, even on these twisted torus knots, will produce L spaces, but whose fundamental groups we don't necessarily know to be left-orderable. So this is another case in which we could sort of tighten this bound and verify the conjecture for even more manifolds if we could find a way to do that. That's all we have for you guys. We'd like to thank Jen Hom and Mike Wong. They've been very helpful in sort of teaching us this summer. We'd like to thank the Columbia RE program for giving us the opportunity to do all this really interesting stuff. And we'd like to thank all of you for sitting here and listening to us. So.
Questions for this one?
Do your techniques apply to groups that have nothing to do with the knots by any chance, or free manifolds?
You can rephrase this in a more group theoretic sense if you just think of like Dane surgery, since we're just modding out this relation, is really just a quotient group. So you can rephrase it a little more group theoretically. The result, if you, yeah, okay, that's
sort of the reason why we think about these knots is that it's very convenient. You know, you saw with this one computation, we can sort of get all the fundamental groups of all the manifolds for these surgeries just by this one computation. So that allows us to generate a lot of free manifolds that we know the fundamental groups of, and that are sort of related, as Ross said, just being quotient groups. So that we use this mostly out of convenience because gives us large classes of 3 manifolds pretty easily. But you certainly could generalize at least the technique if probably also the results in specific cases.
So I think for speakers again.